We know how to do geometry in familiar Euclidean space. But can we also do geometry on thermodynamic state space? Without an intuitive or straightforward notion of what it means for one equilibrium state to be far from another equilibrium state, what we need is a metric on thermodynamic state space. This then gives us a notion of geometry. Now, while there have been a number of proposed metrics, an especially compelling choice is the Rapiner metric, which has its origins in thermodynamic fluctuation theory. The Rapiner metric then provides a notion of length, geodesics, and so on. But most important for our purposes is the meaning of a flat metric. It was shown quite early on that the ideal gas yields a flat Rapiner metric. That is, it is associated with zero curvature. Now, this is a purely mathematical result, but on the other hand, we know that the ideal gas is characterized physically by the absence of interactions. Thus, it was conjectured that curvature indicates the presence of interactions. In this thesis, we take a closer look at the connection between curvature and interactions. And in particular, we ask the question, is the ideal gas uniquely characterized by zero thermodynamic curvature? First, we find that this question is sensitive to whether you regard systems with fixed particle number or fixed volume. Next, we find that the absence of curvature does not necessarily indicate the absence of interactions, and we do this by constructing counterexamples. We did this by two methods. The first was by choosing virial coefficients that describe a gas, and the second was to constrain the form of the thermodynamic response functions, such as the isothermal compressibility and the bulk modulus. Our main result is that vanishing curvature is not a unique property of the ideal gas, but that the ideal gas seems to be privileged in a different sense, which to our knowledge has not yet been described in the literature. For more details, please attend my thesis defense. Thank you.